Hello everyone, today I'm excited to present a groundbreaking energy-based cooperative diffusion model. This work has been accepted as a spotlight paper at the International Conference on Learning Representation 2024. It's the result of collaborative research between Akool, UCLA, and Google DeepMind. In the conventional diffusion model, we follow a diffusion process that adds Gaussian random noise to observed data until the data totally become Gaussian white noise, and then learn the reverse process from noise back to the original data as a generative model. Models like DDPM in the conventional diffusion framework utilize a Gaussian distribution to model the reverse process for each noise level. This approach is acceptable when the additive noise is small, as the reverse process can be approximated by a Gaussian distribution in this situation. To minimize the number of noise levels, or avoid assuming the reverse process as Gaussian, we aim to employ a more complicated distribution to approximate it. In our work, we propose learning an energy-based cooperative model to represent this reverse process. Now let me present our method. We use X to denote an image and T to index the noise level. For each training example, we first obtain a sequence of noisy training examples by a forward diffusion process. The scale alpha and the standard deviation sigma are predefined noise schedule. We use Y to denote X times alpha and define a marginal distribution on Y by an energy-based model, where the energy function is parameterized by the neural network FT. Indexes the noise level. We can derive the reverse denoising process as the denoising EBM, that is the probability of YYT given XT plus 1. Sampling from such a conditional EBM can be performed by Langevin dynamics, which is initialized by the output of an extra denoising initializer. The initializer can be represented a Gaussian distribution with the mean parameterized by a neural network G. The initializer serves as an amortized sampler for the EBM. The denoising EBM and the denoising initializer are jointly trained by cooperative training. In each iteration, we iterate the following 5 steps. We first sample T and training data x0, and then we compute xt plus 1 and yt. Given xt plus 1, the initializer Q generates the initial proposal I hat. I hat is then modified to I tilde by running K Langevin steps guided by the EBM. We update the initializer using the Langevin samples by minimizing the reconstruction error. We update the EBM using the Langevin samples by the contrastive loss. We illustrate the flowchart for the training algorithm. Once the model is trained, we can generate realistic images by sampling from our diffusion model. The sampling process starts from a Gaussian noise and then iterates the cooperative denoising process that first generates a denoising proposal by the initializer and then updates the proposal by K iterations of Langevin sampling. We use 6 noise levels and run 15 Langevin steps for sampling the EBM at each noise level. We demonstrate the performance of our model by comparing it with other baseline methods in terms of FID, where lower FID values indicate better performance. Our model is evaluated on the CFAR10 and ImageNet datasets for the task of unconditional generation. Our model achieves competitive results and stands as a state-of-the-art method among all energy-based models. The model can be used for image inpainting. Given the masked image, we first gradually add noise to the masked image up to the final noise level. We then use the model to denoise the image progressively, similar to the standard generation process, except that only the masked area is updated, while the values in the unmasked area are retained. The figure shown on your right-hand side displays the result. The first 2 rows utilize square masks, while the last 2 rows use irregular masks. The first column displays the original images. The second column shows the masked images. Columns 3 to 6 display inpainted images using different initialization noises. We show that the model can be used for conditional generation. We can apply classifier-free guidance to the model by estimating both conditional and unconditional distributions. We adopt a single neural network to parameterize both conditional and unconditional models, where for the unconditional model, we can simply input a null token for the class condition when outputting the negative energy. By using a similar way, we design the initializer with the classifier-free guidance recipe. Here are some qualitative results for conditional generation. One attractive property of EBMs is compositionality. One can combine multiple EBMs conditioned on individual concepts and renormalize it to create a new distribution conditioned on the intersection of those concepts. Such a compositional generation can work together with classifier-free guidance. The figure illustrates the results of the compositional generation. The left panel generated samples under different attribute compositions. The right panel shows the control attributes. The fitted energy function in CDRL naturally forms a score reflecting the log likelihood of the data. We employ the model trained on CIFAR 10 as a detector and use the energy at the lowest noise level to serve as the out-of-distribution detection (OOD) score. The table displays the performance of our model and some baselines. Our model is competitive when comparing with other models. We briefly summarize the paper. This paper proposes a cooperative diffusion recovery likelihood, CDRL, that tractably and efficiently trains and samples from a sequence of EBMs and MCMC initializers. We demonstrate that CDRL can achieve significant improvements on sample quality compared to existing EBM approaches. We showcase CDRL's ability in various tasks, such as unconditional image generation, image inpainting, conditional generation, compositional generation, and out-of-distribution, OOD detection, etc. For more details, please refer to our paper below. Thanks for your listening.